Well, good morning, folks. This is our June 6th, 6/6 EMX seminar. So greetings from us here at Stanford. And as always, we have two great speakers for our audience today. Before we start, this will be the last of the current academic year, and we'll start again after a few months of summer in the autumn, likely to be October, but we'll give people plenty of notice about that. At this point, I'd like to thank, of course, Raphael and Ziwan, who've provided immense help in getting this together for us, as well as our admins. So I really want to thank them for all they're doing for us. While I need to say that our second speaker will be, who is the inventor of Zed Contrast imaging, although he's the only person on the planet who calls Zed Contrast still, I think, then that will be our Steve Pennycook will give our second talk, but I'll hand it over to my friend and colleague who will introduce the biology speaker. Thanks.
Good, Bob. Thanks so much. Good morning, good afternoon, good evening to everyone in the audience. It's my great pleasure today to introduce our first speaker, Professor Holger Müller, who is a professor in the physics department at University of California, Berkeley. He also have a joint appointment in the Lawrence Berkeley National Laboratory as the faculty scientist in molecular biophysics and integrated bioimaging divisions. Holger originated his education in Germany and he came to America. In fact, he was one of our alumni in Stanford. He worked with Steve Chu before he joined the faculty at Berkeley. And he has been a pioneer in different aspects of atomic, molecular, and optical physics to probe into nature at the utmost sensitivity. I think I have admired his efforts for a number of years. He worked very closely with Professor Bob Glaser at Berkeley to develop the so-called laser faceplate. And this is a new optics in the electron microscope. All the biologists are looking forward. And I would expect that this technology will be a welcome addition to material science as well. So I don't think anyone can match the advances that Holger has advanced. And so it's my great pleasure to have him to share with him his new inventions. And it's a new way of achieving higher image contrast in a transmission electron microscope called laser faceplate. And Holger, welcome, and thanks very much for coming to talk to us this morning.
Thank you so much. Well, thank you so much for being here and for giving me this wonderful opportunity. Let me share my screen and let me go to presentation mode. And there is the knob here. Can you see the slides and can you hear me? Excellent.
Perfectly well, loud and clear.
Excellent. So this talk is about laser-based phase contrast. And being a physicist, I have to start with the obligatory Richard Feynman quote, who said in 1959 that we physicists need to make the electron microscope 100 times better. Unfortunately, he did not specify in which way he wants it to make it better, but fortunately, there's Bob Glaser who specified it, and my slide switching doesn't seem to work. Let me see what's going on here. Fortunately for us, there's Bob Glaser who around 2009 said, let's make a laser-based faceplate for the electron microscope. So we got our marching order. Just one introductory slide. Everyone here knows that single particle cryo-electron microscopy is growing very fast, delivering an explosion of solved structures of proteins. And this basic principle, of course, is that a specimen contains lots and lots of copies of the same protein under different orientations. And from averaging hundreds of thousands of images of these same proteins, a computer can reconstruct a 3D structure. Now, the snag is that this shows the proteins individually and not how they interact in their natural environment. Cryo-electron tomography addresses this problem by taking a tilt series. You make a slice of a cell and you take dozens or hundreds of images under different tilt angles, obtaining a three-dimensional reconstruction of the cell, showing the proteins in their natural environment so you can study how they actually work together. And of course, we all want to cryo-electron tomography to grow equally well, just like single particle EM very soon. Unfortunately, electron microscopy is very far from its theoretical capabilities. Radiation damage and low image contrast make our lives very difficult. The problem is that biological specimens are often what's called a weak phase object. That means they do not absorb electrons very well, leading to low contrast. What they are doing is phase shifting the electron. Let me spend 30 seconds to talk about the wave-particle duality of those electrons, because it will be the key to phase contrast. In quantum mechanics, obviously, an electron is a wave. An electron beam with 300 kilovolts energy has a wavelength of about 2 picometers, right? So what the specimen does, instead of absorbing the electron beam, it phase shifts the electron wave function. So a microscopy technique has to be used that converts this phase modulation into visible image contrast. And the usual method being used in most cryo-EM data taking is defocus. Defocus is a partial way to generate what's called phase contrast. But defocus isn't perfect, and one of the consequences is that atomic resolution can these days only obtained by averaging hundreds of thousands or even millions of asymmetric units, when in theory several thousand should be sufficient. In tomography, the problem gets exacerbated because the already small dose has to be split up among a large number of individual exposures, meaning the individual exposures have very little signal to noise, and that makes it very hard to combine them to a three-dimensional tomographic reconstruction. Okay, on the right-hand side, you see Fritz Zernike, who in the 1930s developed the method of phase contrast in optical microscopy. In optical microscopy, this is therefore a very old method. People use it all the time, and they're not even talking about it anymore. Let me just assert how it works without explaining it, because otherwise we'd be here till tomorrow. In the focal plane of the objective lens, there is a Fourier transform of the specimen. That's true for electron microscopes and for light microscopes. And at the center of this Fourier transform, you see one bright spot that is an image of the electron source. If you're able to phase shift this one bright spot by 90 degrees relative to the rest of the diffraction pattern, then you generate optimal conversion of weak phase modulations into amplitude contrast. So phase contrast is a way to, in principle, extract all the information that is contained in the exit wave after a weak phase object into visible image contrast. Okay. Unfortunately, it has been very hard to implement this in electron microscopy. One of the most successful ways to implement it is the so-called Volta Faceplate. So here's a very coarse schematic of an electron microscope. Don't take it too seriously, but there is a specimen here. Right after the specimen, we have the exit wave. There's an objective lens, and in the focal plane of the objective lens, I insert a thin carbon film. Now, the interaction of the electron beam with the carbon film locally alters the properties of the carbon film, and those alterations produce the 90-degree phase shift. Unfortunately, the phase shift is 90 degrees only sometimes, and most of the time it's not 90 degrees. Here you see a plot of the phase shift caused in an experiment, and you see it starts at 0, then the phase shift builds up as the electron beam starts to interact with the carbon, reaches 90 degrees, and soon exceeds it greatly. And then you have to find a new spot on the Volta faceplate, and the process starts again. So what you can see is, while the effect leads to glorious images sometimes, it is not well controlled, and therefore few labs have successfully used it for cryo-EM reconstruction. I'm a laser physicist, so in laser physics, the solution to any problem is always to use a laser for something. And so we came up with the idea of laser phase contrast. The laser beam creates a, you can see here, the laser beam is coming from the left. There is a lens in the schematic focusing the laser beam down very tightly so that the laser focus overlaps with the focus of the undifracted part of the electron wave function. The interaction of the laser beam with the electron beam works by the so-called ponderomotive potential. The ponderomotive potential can be explained in a hand-wavy way as follows. The laser beam is an oscillating electric field, and that sends the electrons on an oscillating trajectory. Okay. Now, if the laser beam has the same intensity everywhere, then after one cycle of these oscillations, the electron has not moved. It's at the same spot as it would have been without the laser beam. But if the laser beam has an intensity gradient, let's suppose it's brighter on the left than on the right, okay? Then the electron beam experiences a slightly stronger force when its weakly trajectory leads it into the brighter part of the laser beam. And so now there is a net effect, even after averaging one oscillation. And that net effect can be described by the ponderomotive potential. And if you do the quantum mechanics, the ponderomotive potential can lead to the needed phase shift of the electron beam. If that worked, there would be three advantages, and they all arise from the fact that there's now no material whatsoever in the electron beam. In fact, we can move all the components that constitute the laser faceplate millimeters, even centimeters away from the electron beam. And that is great because then there's nothing to interfere with the imaging properties of the microscope. In particular, no material can be charged up. No material will suffer any radiation damage, and the physics of electron-light interactions are very well understood, so this effect can potentially be very well controlled. Then why hasn't somebody done this long ago? The problem is we need 75,000 watts of laser radiation focused to 8 micron to make to phase shift a 300 kilovolt electron beam. Picture that. There is essentially 75,000 watts is a lot of power, right? And it's focused to 8 microns. So what we're talking about here is the brightest laser focus that has ever been made anywhere with a continuous laser. This isn't easy, okay? Pulse lasers can reach these intensities fairly easily, but usual electron microscopes are continuous, so we need a continuous laser. To put it in context, on the left, you see one of the largest lasers that are commercially available for things like welding and drilling. It's a 10,000 watt industrial laser made by IPG Photonics, but they need a lot of room. They are expensive, and we would need 7 or 8 of those. The military has stronger lasers, but they are potentially unsafe and still not powerful enough to make a laser faceplate. So what are we to do? One of the first ideas by Brian Reed, who is now running a company called IDES Corporation, had the idea of using a pulse laser interacting with a pulsed electron beam in a pulsed microscope. And this idea is now being picked up by the Anthony Fitzpatrick lab at Columbia University. But there are challenges that we noted when we started our project about 10 years ago. As many people in the audience know much better than me, pulsed electron microscopes don't perform quite as well as continuous ones. That's a first problem. And a second problem is we need to synchronize very well the laser pulses with the electron pulses, and that can lead to its own issues. So instead of tackling these issues, we decided to use another method that my lab was very familiar with, using a Fabry-Perot cavity to build up a lot of intensity from a reasonably powered laser. So here is a principle of the laser faceplate. I want to direct your attention first to the little schematic on the right. If I take a laser beam and confine it between two mirrors, the laser beam can make, for example, 10,000 round trips, building up 10,000 times the intensity that the original laser beam had. So here's a schematic of the microscope. There's the specimen here. Lenses are symbolized by these current loops. There's a focal plane right after the objective lens, but unfortunately, and you see the green electron beam has a focal point here, right? But unfortunately, two things prevent us from putting the laser faceplate right here. The first is physical space. The objective aperture is crammed, okay? The second is that the focal length of the objective lens is quite short, 3.5 millimeters in our scope. And that means this unscattered focal spot is very small, making it hard to match the size of the laser focus to the size of the electron focus. So we use the Lorentz lens to generate a second diffraction plane down here, where we have more physical space. And this diffraction spot is about 5 or 6 times magnified relative to the original one, making it easier for us to integrate our laser cavity. So laser enters from here to ultra high reflectivity, ultra low loss mirrors, build up about 10,000 times the laser power and generate the standing wave pattern, and the central most bright spot, in theory at least, should interact with the undiffracted part of the electron beam. Now, one possible objection to this scheme is we wanted one spot that gets phase shifted, but instead we get this entire chain of spots that gets phase shifted. And we will look at how this affects the imaging properties a little later in this talk. Suffice it to say for now that the effects are relatively mild, and we've simulated that this can leave near perfect phase contrast. In fact, at realistic signal to noise ratios, it is very hard to distinguish from perfect phase contrast. Here's another artist's impression of the thing. The laser cavity is here, but notice the two graphs here. This one shows the measured cavity power versus time, and you can see it stays constant for 120,000 watts, 120,000 watts circulating in this cavity until we turn it off 10 hours later with no apparent drift or deterioration whatsoever. In fact, our faceplate has accumulated hundreds of hours of operation and shows no deterioration. On the right-hand side, you see the contrast transfer function. Ideally, we want to see it close to 1 or -1 over all spatial frequencies. And you can see that the contrast transfer function is high over a large range, several orders of magnitude of spatial frequencies, limited at high resolution by the aberrations of the scope. We'll talk about that more later. One figure that I want to brag about shortly is the radiation. The intensity is so high that the radiation pressure here at the focus is about 100 atmospheres. So this is great. But as we will see in the rest of this talk, it is currently limited by aberrations and low sample throughput in our relatively old low-base Titan microscope. This can be addressed by developing a miniature faceplate that we could insert directly into the back focal plane, foregoing the use of this relay optics, or by building a special Krios microscope with aberration correction to work around these aberrations. And I will talk about these two solutions. Okay, first let's take a look at how the cavity is designed. I want to not spend much time on it, just notice that the mirrors are here. It is really extremely hard for the optical industry to make these mirrors. This is really state of the art, and the supply chain takes about a year. If we place an order for new mirrors now, we'll have them at hand in only a year, because the combination of extremely flat polishes or extremely smooth polishes and relatively short radius of curvature is hard to achieve. The other feature I want you to note is that this whole thing is engineered to fit into a 1-inch port in the microscope column, and the electron beam has to pass through a 2 millimeter hole here. That will become relevant later. At these high intensities, you can imagine that a single speck of dust burns into the mirrors very fast. So this whole thing has to be assembled under clean room conditions. And then it's being integrated underneath the octagon, underneath the objective lens. And the cavity sits at the end of this holder, and the laser beam enters from here. Here's how the thing looks like in the lab. This is our Titan microscope. This 19-inch rack holds the lasers. The laser beam arrives through this fiber on an input coupling breadboard, which has mode matching optics to get the beam into the microscope column, where the pair of mirrors is. And the spent beam is analyzed on the right. That allows us to run feedback controls to keep the cavity aligned. Okay. When we first turned this on, our laser beam was not perfectly aligned with the electron focus. And what you then get is a so-called ranchigram that you can see here on the right. This is one-to-one the data as it came from the camera, unprocessed and all. And the streak through, you can see, is actually an image of the light wave. If we bring the beam closer to focus, this feature gets magnified and looks like the one on the right. This is great for physicists to see because we're imaging light using electrons rather than the other way around. But it's also useful. We use these ranchigrams to characterize the intensity and position of our laser beam. And this is an important part of auto-aligning the laser beam with the electron beam. Since these look great, let's take a look at some blown-up versions of the image of the laser beam. And Jeremy Axelrod, the grad student on the project, has taken these images, and they won a prize by the Wikimedia Science Foundation, so you can see these images online. All right. Another of the great ideas that Jeremy had was that for a relativistic electron beam with an energy of more than 211 kilovolt, the ponderomotive effect can actually be inverted. Instead of being repulsive, repelling the electrons from the antinodes of the beam, it can be made attractive, okay? And this has been theorized for a long time, but proven by Jeremy for the first time, who used a wave plate to change the polarization of our laser beam and demonstrated this relativistic reversal. The use of that is, on the left, you see an image of lacy carbon taken with our phase contrast microscope, and it shows ghost images here that are, of course, unwanted. By setting the polarization to the relativistic reversal angle, you can make the ghost images disappear. So this is a very nice demonstration of physics, but it's also very useful in the context of phase contrast imaging. Okay. Can we image biological specimens as well? Yes, we can. On the left-hand side, you see Rubisco, and on the right-hand side, you see 20S proteasome. By the way, Yifan Cheng was very nice in making specimens for us. Thank you, Yifan, in case you're here. On the left-hand side, you see images without the laser operating. On the right, you see a different spot of the same grid with the laser on. Both panels use the same defocus, same exposure, and so on. And you can see the contrast enhancement caused by the Llpp laser faceplate quite clearly. From these images, we performed a complete reconstruction of these proteasome particles, and we're quite happy. That happened about 2 years ago. But limitations were apparent. Unfortunately, these reconstructions do not represent a record in terms of particle number or resolution or particle size or what have you. What are the reasons for these limitations? Well, the first is chromatic aberration, as expected, because the relay optics that we're using causes a little bit of extra chromatic aberration, and that is going to affect the resolution. Second, also expected, was ice contamination, and our Titan microscope is slightly worse than in a state-of-the-art Krios. But unfortunately, what we found is it's not just slightly worse, it was much worse. And the third was a complete surprise to us, it's Johnson noise. So here on the right, you see our initial measurements, they were refined later, of the contrast transfer function envelope as function of spatial frequencies, you see the dotted lines are theory curves, and you see the laser faceplate as installed performed much worse than theory. So what are we supposed to do? Well, it turned out after a lot of painful guesswork that Johnson noise was responsible for that. Remember that little 2 millimeter hole that the electron beam has to pass? Well, the electrons inside the metal walls of this hole are at room temperature. They are moving around thermally, and that causes random magnetic fields that cause random electron reflection and therefore resolution limit of the image. Jeremy developed a method of computing these things that I won't go into. And it turns out that with these Johnson noise effects, we could perfectly model the effects that are going on in our microscope, and we also take into account CC, chromatic aberration. The solution to that is easy on paper, but a lot of work and practice. We need to increase the diameter of the hole. So here you see measurement and theory for a 2 millimeter hole line up extremely well. And as the hole size is increased to 4 millimeter and 8, the performance of the laser faceplate installed is nearly indistinguishable from the performance of the microscope without the laser faceplate. So a low noise laser faceplate is now being manufactured. Here you see the design is essentially the same as the old one, but the hole is increased. And here you can see how it looks like on the CNC in the Berkeley Physics machine shop. We are right now assembling this, installing the mirrors into it, and we hope to have it inside the microscope very soon. Here you can see how it's being assembled. And again, it all has to happen under clean room conditions. So we have to be very careful, and these operations take a long time. We've also tamed the ice contamination of the Titan by additional pumping stages and by using an objective aperture that is large enough to not affect the imaging properties of the microscope, but small enough to block most of the ice. And that has reduced the ice buildup rate about 10 times, where it's still not as good as in a Krios, but good enough for us to take data. And the final limitation was the increased chromatic aberration of our relay optics. We have now installed a monochromator and turned it on and have shown first signs of life of it. That will overcome the increased chromatic aberration by just decreasing the energy spread of the electron beam. So we hope to have very good images very soon. We're collaborating with Thermo Fisher Advanced Technology to make a Krios microscope with a laser faceplate. The idea is to make it available to the community of electron microscopists so that it can have maximum impact. But electron microscopes are expensive. So is it possible to really put a laser faceplate directly into the back focal plane? And my postdoc, Peter Petrov, who graduated from W.E. Myrna's lab at Stanford, is working on significant miniaturization of the laser faceplate. And we have received the first miniaturized mirrors, so we hope to have progress there very soon. This would be very appealing also because it gets around the need for relay optics. The other approach is to go the opposite way and make the thing bigger. And the Chan Zuckerberg initiative makes this possible, to add a laser faceplate to a custom Krios microscope. And this will have all the bells and whistles that you would want to see. It has an autoloader and a cryo box for making high throughput imaging possible, a monochromator and a CS corrector to offset the aberrations of the relay optics. It has an energy filter for tomography and the latest generation camera. And the goal really is to reach a resolution of 1 angstrom with the system. Will Johnson noise hurt this? And it turns out by increasing the diameter of the beam liner tube, the CZI microscope can still reach a contrast transfer function that is larger than 0.5 at 1/1 angstrom spatial frequency. Despite the Johnson noise issue. We're extremely grateful for Thermo Fisher to be so collaborative and consider these modifications. All right. The CZI microscope will also feature a dual laser faceplate that will, and here you see the simulated contrast transfer function of our Titan. So bright is better, dark means no contrast. And you can see that the contrast drops rather quickly at high spatial frequency from aberrations. These will be GAN with monochromation and aberration corrections. The rings in the spatial contrast transfer function will also be GAN. And finally, you see the streak here. This streak is the consequence of the linear geometry of the laser beam. Using dual laser faceplates replaces the one streak by two streaks. You would think that is worse, but these two streaks are much, much less pronounced. So that addresses this issue. And so what are the current plans? Here you can see a picture of the partially built CZI microscope in the factory at Eindhoven. Here are some examples of collaborations that are waiting for the microscope to be delivered. With Jim Hurley, we want to explore HIV pathogenesis. And with the David Rubin lab, we want to work on clathrin-mediated endocytosis and the influence of membrane curvature. And finally, we hope that we can collaborate with Bronwyn Lucas on exhaustive template matching. We will now demonstrate the low noise laser faceplate with the large bore in our Titan microscope. We're manufacturing the plates for the CZI microscopes. And finally, as a last slide, if I have dual laser faceplates whose phase shift can be varied at will, that offers new imaging modalities that we're studying together with our postdoc, Peter Petrov. Here you see some simulations of the point spread function for that as applied to imaging a carbon atom. And this is standard mode. This is with aberration correction. You can see the higher numerical aperture leads to sharper features. And this is with phase contrast. And you see this very sharp feature at the center of the point spread function. And this leads to simulated images of myoglobin. So we hope that soon the CZI microscope will allow us to study this. I am indebted to many, many people at Berkeley. The current team consists of the graduate student Jeremy Axelrod, who has worked with Osip Schwartz, who was the postdoc of the first hour to make this happen. Peter Petrov, I already mentioned, is the postdoc who joins us from W. Myrna's group. He's working on miniaturization and simulating new imaging modalities. Then there are undergraduates, Shahar Sandhaus and Carson, and also our brilliant technician, Jonathan Remis. I want to thank Robert Glaser for his continued collaboration and for originating this project, and Eva Nogales for helping us quietly behind the scenes without us even noticing. And I want to thank you all very much for your attention.
Thank you very much, Holger, for these really exciting advances and share with us about the fundamentals of your new laser faceplate. It's truly promising from what you described this morning. And there are a few questions from the audience. The first question is, what is the wavelength of the laser? And also the cavity Q, finesse, and Llpp of the mirrors?
Yeah, the wavelength is 1064 nanometers, just because lasers with good properties are available at that wavelength. In principle, the wavelength doesn't matter much. The finesse is 30,000. The power build-up factor is theoretically the finesse over pi, so we'd expect 10,000. In practice, we reach about 8,000. The radius of curvature of the current implementation is 20 millimeters. We're working on making this shorter. The threshold of pain for the manufacturer seems to be 5 millimeters.
Okay, thank you. And then the next question is, can we cool the Airtime optical column and make it longer rather than wider to partially compensate for the Johnson quantum noise?
So we could, in principle, cool it. that would solve the problem. I know people at LBL are talking about cooling the entire microscope to get rid of this problem entirely. But for us, there was really no reason why the hole was 2 millimeters. We just didn't know better. So it is not very hard to make the hole 8 millimeters. So for us, that turned out to be a much easier path to resolving the issue. But yes, in principle, it's right. If you can cool the machinery, Johnson noise will go down.
Good. How cold this has to be?
Let's see. So we're increasing the hole diameter fourfold, achieving a fourfold reduction of the random deflections. So to get the same, you would have to reduce the temperature fourfold to 50 Kelvin. I suppose 77 Kelvin would do the trick.
Okay, good. Thank you. And then the next question is, which laser wavelength is optimum for Llpp? And what is the laser wavelength dependence of the airtime beam phase shift?
Yes, so for constant intensity, the phase shift is proportional to the constant intensity and constant geometry, like the focus size is the same. The phase shift is proportional to the wavelength. So a longer wavelength allows you to use lower intensity. Unfortunately, even at 1064 nanometers, it is already hard to focus the laser beam to a few microns inside the cavity because of the difficulty of making mirrors with very small radius of curvature. So going to a longer wavelength would make that more difficult. In principle, it would be desirable to use a shorter wavelength, but then it will be harder to get mirrors of the same low loss, and you would need more power. So we think 1064 is, but as I said, the laser wavelength is not extremely critical. For example, at 1.5 micron wavelength, I think it would work just as well.
Good, thank you.
There's a question come in from Richard Henderson on the chat.
Yes, I do see that. Richard's question is, do you have enough money to develop laser faceplate into a commercial product?
Thank you, Richard, for that wonderful question. So the very short answer is no, but let me qualify that. We are physicists and biologists. We are not the perfect people to develop it into a commercial product. We would have to either fund our own company to do it or collaborate with an existing company to do it, right? So I see my role currently as demonstrating the technology, bring it to a level where the engineers can take over and let them do their engineering then. Yeah.
Good.
So that's how I see the situation.
Okay, that means there's business opportunity for the audience.
Right.
All right, good. And another question asks, if one is not really keen to have a atomic resolutions, can we make it cheaper and easier to do? You know, if one is happy to settle with 3 angstrom resolution, can we make a cheaper instrument?
Yeah, I think the path to make it, so our implementation in the Titan has 2 reasons why it's not the perfect implementation. First, it still needs the extra relay optics. That means it's expensive. And second, the relay optics causes CC and CS aberrations. That means you would need a monochromator and a corrector to overcome this. So the key to making this affordable, I see in the miniaturization project. If we could stick the miniaturized faceplate directly into the objective aperture at the point where now the objective aperture rod is, right? Then one could, in principle, use a standard Krios or Titan microscope, perhaps with slight modifications, slightly modified objective lens, right? We at Berkeley don't want to go all the way. We want to miniaturize it to 4 by 4 millimeters rather than the required 1 by 4 millimeters. But if that works, I think then this shows that we're on the right track. And a slightly modified objective lens can accommodate this. By the way, I want to give a shout out to my former postdoc, Osip Schwartz, who is looking into that at Weizmann Institute. And what I could imagine is that a company such as Thermo Fisher might be interested in developing a microscope based on this miniaturized or semi-miniaturized faceplate, because it would be much easier than the CZI approach, which is to essentially attach more elements to the microscope.
Good, thanks. Another question being raised is, can we still get enough image contrast with a laser faceplate with zero defocus?
Yes, this is something I wanted to keep secret, but let me, where is a good contrast? Well, I don't find a good slide for that, but if it was possible to reliably dial in zero defocus, and this is not at all trivial, we could talk about having a sacrificial part of the specimen which we sacrifice in order to adjust the focus and then image the rest of the specimen. There will be one plane in the specimen where the defocus is zero, and that leads to a flat contrast transfer function, which is very close to 1 over a very large range of spatial frequencies. In principle, we do not lose any information because the contrast transfer function doesn't have any zeros anymore, right? And this will be enabled by the combination of laser phase contrast and spherical aberration correction. Now, because of the difficulty of really dialing in zero defocus, I do not advertise this currently, but I hope that one day somebody can make it happen. Let me mention another thing. With aberration correction, the depth of field of the phase contrast microscope is actually very small and can be smaller than the thickness of the specimen. And that helps us to look at alternatives to tilt series by, for example, replacing a tilt series partially with a through focal series as they do in light microscopy. So this is all very exciting. So that question was right on the money. Thank you very much.
Okay. And other questions being raised is, could you use a laser before the sample? In other words, in the front focal plane of the lens, to increase the phase contrast for scanning transmission electron microscope operations?
Given infinite time and resources, I would love to look into that, but we haven't done that simply because we have our hands full with the faceplate after the specimen. But yes, I know that people have been talking about these ideas, and I hope that somebody will try it out.
Great. And another question is, how do you couple the light into the Llpp cavity efficiently?
By asking Jeremy and the others to do it, and they are just so good at it. I did high finesse cavities for my PhD, and we were happy to get coupling efficiencies of 30%. But the people in the laser faceplate lab, they're able to get 80 or 90%. This is amazing. They've worked very hard and very long at that. Now, two things happen. When the laser runs for a while, the cavity heats up and the mirrors change their shape slightly. And that affects the coupling efficiency and the size of the focus. So there's a feedback loop that measures the size of the focus by characterizing the spent laser beam. And that can, in principle, apply feedback changing the cavity length to keep the coupling efficiency high despite these radius of curvature changes. So there is a whole slate of engineering that I haven't even talked about. Another one is optomechanics. The laser radiation pressure is pushing against the mirrors, and that can lead to instabilities. Fortunately, this has worked out relatively well. And one of the key ideas here is to make the mirrors out of so-called ultra-low expansion glass ceramics, which has nearly zero coefficient of thermal expansion. That alleviates all these things a lot. So there's a lot of engineering and getting good numbers here.
Okay, there are remaining quite a number of questions, and I'd like to hold off the questions until our next speaker. So if the audience can stay online, so we'll continue the discussions afterward. Again, Holger, thank you very much for these stimulating lectures. Okay, I turn it back to Bob.
Okay, thank you very much, Holger. And I'm glad there was a STEM question at the end, as it'll be mainly a STEM talk that that the next speaker will be giving. So our colleague, Professor Llpp, who's currently in New York, I believe, will introduce Steve Pennycook. Yi, please.
Yeah, thank you, Bob. Well, thank you, Holger, first, for telling us about this very exciting tool. Now let me introduce the next speaker, Stephen Pennycook. Stephen is a world-leading microscopist, a pioneer of STEM, and he laid the foundation of both theoretical and experimental modern electron microscopy, particularly for the Zed Contrast technique. And he also played a leadership role in developing sub-angstrom resolution aberration corrected electron microscopy. Well, Stephen has a lot of awards, let me mention. Well, he's a fellow of American Physical Society, American Association for the Advancement of Science, and a fellow of Microscopy of America Institute, a fellow Institute of Physics, also MIS as well. 92, he won MIS medal, and 2012, he won the MIS Innovation and Characterization Award. Without further ado, Stephen, please tell us about your very exciting research I have been following for a long time, please.
Okay, well, thank you very much for that kind introduction, and thanks to Bob for the opportunity. Let me see if I can share my screen here. Oh, here we go. Yes, so this is going to be the story from Z to A, Zed Contrast Guide to the Atomic World. Although, as Bob pointed out, where we come from, people call it Zed Contrast. But yes, it's great to be able to tell you this story, how it all happened. And actually, it all happened a long time ago, in a far off land. Just a second, let me get rid of that. When a young man was at University of Cambridge, I'm sorry, let me just try and get rid of these thumbnails. Here we go. Not at King's College as here, but at a much less grand place, Sydney Sussex College. But I did manage to learn to punt along the river while I was undergraduate. And then I stayed for a PhD, and this is really where it all started. Now, my PhD was not about atomic resolution imaging in any way. It was cathodoluminescence on the stem. It's, you can see what I did was I built a little light collection device down around the sample, and you could get stem images, diffraction contrast, annular dark field images showing defects in diamond, and correlate with light emission. And you can see some are bright, some are dark. Now, I never actually figured out why, because the cathodoluminescence is far more sensitive to impurities than EDX or X-ray analysis, for example, or eels. But how did the Zed contrast come around? This was with my student, Mike Tracy, who was doing his thesis at the same time, and his supervisor was Archie Howitt. And he was having trouble seeing these tiny catalyst particles in bright field. because of diffraction contrast, especially on gamma alumina, crystalline supports. And so he had this idea, why not go to high angles when that diffraction contrast should be replaced by thermal diffuse scattering. So I built a little detector to replace my mirror. And this was the first high angle annular dark field, one of the first images ever achieved. And you can see it does nicely show the contrast from the particles. And thinking about it, of course, the high angle scattering is generated incoherently by hitting the atoms. It's thermal diffuse scattering. So it's generated incoherently. It depends on the intensity of the beam hitting the sample, which is exactly what photoluminescence was. These are incoherent signals. Well, okay. I then, in 1982, moved to Oak Ridge, took up staff position in a group of Jagdish Narayan, and he said he would make me a semiconductor man. Well, he was looking at ion implanted semiconductors like silicon, and I had forwent my HP5 for a Philips EM400, but I did at least have a stem attachment. So I was able to do a little stem and follow this idea of trying to do Zed contrast. So I kind of became a semiconductor man doing Zed contrast on the side. But you can see with the Philips, we actually could get to a high angle detector just by going to a low camera length. And so here you have a regular TEM image of a cross section antimony planted silicon. You can see damage or defects in the near surface region, end of range damage. And in the regular ADF stem, low angle ADF stem, you still see the diffraction contrast dominates. But if you go to high angles, you see it completely changes. The diffraction contrast goes away. And what you see here is actually the dopant profile. This is the implanted antimony. And the profile from the image matches the EDX profile and also the profile known from Rutherford backscattering. So this was really the start of the Zed contrast and what put the seed of atomic resolution into my head. And I thought, well, it's incoherently generated. It means you get scattering when you hit the atom, and if you're not on the atom, you don't get scattering. It should be an incoherent, directly interpretable image. So I published that idea in 1986. Should be entirely complementary to conventional high resolution structure imaging. Surely it had to be possible. Well, this was 86 and unknown to me at the time. This was when we did not have internet but John Cowley at ASU actually had an HP5 with a high resolution pole piece. It was not a VG microscope's pole piece. It was a JOL pole piece actually, but he produced this pair of images and he commented that the annular dark fielding image shows the expected increased spatial resolution. And that's basically what he said. And he didn't mention, although he must have changed the focus, this is a phase contrast image. This will reverse contrast, as you know. This would not have changed contrast. But he didn't say anything about that, which is kind of surprising. And I never really talked to him about that. But I realized there was this feeling amongst people who did imaging lattice resolution that incoherent imaging was supposed to be impossible. Well, luckily I didn't know that. And neither did the Department of Energy know that. So I was lucky enough to get this HP501 funded, and here it is arriving or set up in Oak Ridge. This is me, by the way. And yeah, so we could try it out. And actually it worked pretty well, considering we had about a 2 angstrom beam at that time. And that was when Lynn Boatner was actually making these high TC superconductors. And you could see the contrast in the image from YBCO with yttrium on this plane. Matches pretty well the simulations. And you replace that yttrium with erbium, the center line goes bright. So it seemed to work. We tried silicon. This is just a comparison of a regular TEM taken on 200CX. Thin germanium film on silicon. And this, of course, is a structure image. So you don't get Zed contrast when it's very thin. Only when it's thicker, you get absorption contrast. But on the stem, annular dark field image here. Very nice image of contrast between the germanium and the silicon. And you can see this interface very nicely. You can see this interface very nicely as well. No speckle pattern from the SiO2. Certainly looked like a nice incoherent Z contrast image. And actually, if you look really closely, although this is poor resolution by today's standards, put the structure on there, you can see these features are not circles. You can actually interpret the elongation to indicate there must be two or at least two columns of atoms spaced below the resolution limit. So this is a characteristic of incoherent imaging. It maintains interpretability even beyond the resolution limit. Here you have thickness fringes in silicon 110, interference image and bright field, and in dark field here, practically no sign of the interference at all. And this is convenient. You can look at the image at all of these different thicknesses, and basically it doesn't change in form. So that was the birth of incoherent imaging. Now, Dave Jessen joined me around this time. We wanted to know how this really worked. How could you have a incoherent image in one signal and all this interference going on in the other? There was this theory that to get an incoherent image, you had to collect all the scattered electrons, including those coming through the whole of the objective aperture. So that's why it was thought to be impossible. But Dave, or we worked out, in fact, that you don't need all of the electrons. You just need to sample enough. You just need to average the diffraction pattern over a large annular detector. So you cut a big hole in it and all these cross terms disappear. And you get an incoherent image, some of the intensity scattered from the different atoms. Well, that's not the end of the story. Of course, you've got thickness to think about. That gives you incoherence in the plane of the detector, transverse incoherence. If you make a column of atoms and you calculate the scattering on the annular detector, you'll find that there is coherent interference between atoms at different heights. So this is the thickness dependence from coherent scattering, but actually atoms are not stationary. Let them vibrate. Thermal diffuse scattering, after all, they are vibrating. And so if you turn on phonon scattering, you see you get a little bit of residual coherent interference, but basically the signal then increases almost linearly with the number of atoms. Well, there's one other factor to consider, and that's dynamical diffraction. And that we also figured out that in HREM, for example, the silicon fringes change with thickness primarily because of the interference between these block states, the 1s and the 2s. And that really explains the thickness dependence and contrast reversals. But if you're looking at it with a high angle annular detector, only the intensity near the atoms matters, and the other block states effectively are filtered out, don't contribute to the image. And that kind of nicely explains why incoherence is maintained under dynamical diffraction. Well, oh yes, and Nigel Browning, not to forget Nigel, came over to try atomic resolution energy loss spectroscopy. And this was a beautiful sample provided by Matt Chisholm, cobalt silicide, epitaxial on silicon. And although the image is horrible by today's standards, you can definitely see that it is an abrupt interface. And if you do the eels, you see the cobalt edge does disappear across from this plane to this plane, which is about 2.7 angstroms, and we had a 2 angstrom probe. So that looked good. So let's move to some applications. We had a visit from Binayak Dravid, and he brought this beautiful sample of a bicrystal of strontium titanate. And there were lots of models of the grain boundary structure. And this was the way it was done. When you had phase contrast image, you would build various models and see which matched the simulated, which model matched the experimental image. Well, in our case, we just took a Z contrast or Z contrast image, and it's very easy to see these columns. This is sharpened up a little bit with maximum entropy. Of course, in those days, we couldn't see the oxygens, but we could see the cations and distinguish the strontiums from the titaniums. And the structures we saw at the grain boundary were not like any of the previous models. And so that's where we got this often applied phrase, structure was more complicated than previously thought. But it's quite easy to see how the grain boundary is built. This was a 920 grain boundary plane. And you can see it was basically built with these structural units, these sort of double columns, very closely spaced, and made of segments, 410 and 510. And you just put in extra spacer unit here, highly distorted, but just separate out these dislocation cores, and you can build the boundary at whatever angle you like. At larger angles, you would come to need 110 type dislocation cores, this kind of structural unit. But essentially, this rather nicely proves the continuity of boundary structure. All except around 45 degrees, actually, where you could predict the structure of a straight grain boundary, but nature had different ideas and faceted these boundaries into asymmetric 100 and 110 segments. So we did look at asymmetric boundaries as well, and they also follow a structural unit model. Well, the Department of Energy seemed pretty happy and seemed willing to fund a higher resolution microscope, 300 kilovolt. STEM was, there were a few of these being built for various places, and I managed to get funding for one and persuaded VG to accept the high resolution specification, and they produced, and then we were able to properly resolve the dumbbells in the 110 orientation of silicon. In gallium arsenide, we could distinguish arsenic from gallium based on the Zed contrast. So this was very nice. Pete Nellis was there at the time, and of course, Pete, never satisfied with splitting the dumbbell, had to go and try and go sub-angstrom. And indeed, he did go sub-angstrom. You can see the transfer here. He did it by going to a large underfocus and got information transfer to 0.78 angstrom. The image was pretty noisy, but clearly elongated pairs of atoms. So kind of resolution of a sort. And we realized, in fact, that the conventional resolution limit in a TEM, you'll cut it off with these damping factors. But in STEM, it's really quite different. We have the high resolution information is not cut off by things like energy spread or defocus spread. It's the mid-range frequencies that are damped. So very different behavior. High resolution information is preserved. So carrying on with the story, our favorite material, strontium titanate. We figured out eventually that these so-called, these pairs of columns, it was pretty obvious they couldn't be fully filled because they were too close together in the dislocation cores. And Sok Pantelides became a regular visitor to my group, doing density functional theory, and Myung was also a postdoc, also doing density functional theory. Eventually we realized that it's the non-stoichiometry at the grain boundary that is the origin of the electrical activity. And so you deplete the boundary of oxygens and you get positive charge left behind, setting up band bending and a depletion layer. Well, I already mentioned high TC superconductors one time. This is actually an image. It looks very like strontium titanate, but it's actually YBCO, grown epitaxy on strontium titanate bicrystal. The amazing thing, or at least it was amazing at the time, of course, this is derived from the perovskite structure, so maybe it should not be so surprising that the units we saw in these boundaries were actually identical to what we'd seen in strontium titanate. And that was true not only for those symmetric boundaries, also for asymmetric boundaries. The units and the structural sequence identical to strontium titanate. Now, at this time, there were these intriguing results on grain boundaries and critical currents coming out of Germany, Hilgenkamp and Manhart, for example. They were plotting the critical current across these bicrystals as function of orientation. And they found that it went down exponentially. So grain boundaries were absolute disaster for superconductors. Well, we thought for a few years, in fact, we know the structure of these boundaries because we can predict them. We know what kind of units they are, and the number of units goes up with misorientation angle like this. Let's assume 2 electrons non-stoichiometry per unit, for example, and let's plot the depletion zone. And since the number of units goes up linearly, so does the width of the depletion zone. Goes up linearly, and a supercurrent is going to tunnel across that. And so it's pretty natural. If you have a tunneling effect, the critical current is going to go down exponentially. So we were pretty happy to see this fit between their results and our structural unit model prediction. Okay, well, moving ahead, this is where Andrei Krivenek enters the scene, and this is my beloved VG-HB501. He said, "Steve, you need an aberration corrector." So I said, okay. Remember, at this time we had the 603, but it was still a fairly traumatic time, except Andre came through and it worked. And the 501 now was able to split dumbbells just as well as the uncorrected HB603. So it was very impressive. This is Andy Lupini, a postdoc at the time. I knew we were seeing bismuth atoms because they were moving as the sample drifted. So that was quite exciting. Maria Varela was there also at the time. She used the machine to find single atoms of lanthanum. And you could see them in the image and you could identify them in the eels, even with atomic resolution. Pete Nellis came back from time to time. He came back when we had an aberration corrector, again, thanks to Andre, on the VG HB603. And actually, you'll notice here, Pete can reach this top aperture by standing on the floor, whereas this is Bill, the technician, and most of us had to stand on a step stool. Well, and with Matt Chisholm, they managed to get, this is silicon in the 112 orientation. So these dumbbells are actually just 0.78 angstrom apart. And it's a little bit noisy, but if you clean it up, you can really see all the dumbbells are actually nicely split. So this is very clear resolution from silicon 112. Well, the other thing we found was that the bright field image, we were able to open up that collector aperture and get really good signal, and simultaneously. And if you watch, when this one, let's play that through again, when this one goes through its contrast reversal around here, this Zed contrast image, this is when all the single atoms around the edge are beautifully in focus. So very nice to have the phase contrast simultaneously with the Z contrast. There it goes again. Well, some of the exciting things we were able to look at then, we had Jan for Jan and AJ Abe came as postdocs and fellows. And before aberration correction, you could sort of see the Penrose tiling pattern here, but not quite see all the atoms. Now let's just turn on the aberration corrector, and all of a sudden, these inner rings are nicely resolved, and we can see the structure. Look at this one here. You can see it's twofold symmetric, not 5 or 10-fold symmetric. We could get the structure, and we could see the origin of the matching rules, the origin of the quasi-crystalline structure. Quite satisfying. Noe Shibata, this is Yuichi Ikahara from his group in Japan, sent Noya. I think he was a student at this time, or might have been a JSPS fellow. Now I can't remember. But he brought these beautiful samples of rare earth doped silicon nitride, and you could see the very different structures at the different interfaces, different structures with different elements. But the rare earth was always nicely attached to the silicon nitride, and it not been possible to see those clearly before. The other thing we realized is Albino Bericevic depth resolution, as mentioned in the previous talk actually. If you increase the angle, then depth resolution increases as the square of the angle. So it's dramatic increase, especially if you go to a 5th order corrector. And now you can probe different heights of the sample. You can focus on the top and the bottom and look at the circle here. This is Klaus van Bentham. Focusing through the dielectric, there we are. The hafnium atom comes into focus and disappears. We're just going 0.5 nanometer at a time here. But he was able to map all these dopants in 3 dimensions. You can see there's quite a high density. So Pandelides with a student worked on the wave function here. Showed that this density, the wave function would overlap and you would get leakage. And this would explain rather nicely why the device was too leaky to be of use, too many stray hafnium atoms. Sang Ho was a postdoc at the time. He produced or found this nice nanowire sample. You can see it's got gold on the surface, but we could look inside. You could see the top surface and the bottom surface as you change defocus. So these are images from slices inside, and you can see substitutional gold here, interstitial gold here, here and here. And again, with some density functional theory, you could actually confirm that all these positions that we saw in the image were actually stable. So rather exciting. Well, the next big development was Andre again with his UltraStem. This is a 5th order corrected machine. And this was the famous boron nitride, the imaging of oxygen and carbon impurities at just a 60 kV. So no longer needing heavy atoms, now we could image even fairly light atoms. And actually the guy who did this cover at the same time, I said Sok Pandelides liked to send his students to the group and get them to learn microscopy. Well, this is one of them here, someone I know pretty well. My son, Tim, was actually in the group, a student of SOC, and we set him this challenge. Previously, we saw that it's been found that thin layers of YSZ, epitaxial with strontium titanate, showed this remarkably enhanced ionic conductivity. Well, Tim produced quantum molecular dynamics to show that this was actually due to the oxygen sublattice melting. Because it was under this tensile strain, lattice was expanded and there was a mismatch at the interface. It appeared that this melted. And he also went on the ultrastem. You could see mapping oxygen here in yellow. It kind of washes out. Looks very like a liquid in the thin YSC layer. Well, he also, another problem out of Vanderbilt were these white light nanocrystals. They discovered when they got small enough, instead of having a fixed blue, they were aiming for a nice blue, deep blue. What happened? They got white emission, even from individual nanocrystals. And when you put them in the microscope, or when Tim put them in the microscope, this is what he saw. No fixed structure, they were continuously evolving, and he was able to do the DFT and showed that as it evolved, again with quantum molecular dynamics on a cluster, he could show that those fluctuations, he heated it up to about 500 degrees, and again got this white light emission as an average over time. Rather satisfying result there. Ryo Ishikawa was also sent by Yuichi Akahara as a JSPS fellow. Again, he could tell, he could track diffusion. This is cerium atoms in aluminium nitride. And let's see where it starts again. You can track it along this, oops, not going to start again. You can track it along this line here. And he could again tell by focusing on the top and bottom surface that this was indeed internal diffusion. He could get the mechanisms. He could even locate it in 3 dimensions. I think I'm running out of time here. Wuzhou was able to do atomic resolution eels. Juan Carlos, also working on graphene. These are impurities, doped. And you can distinguish, the fine structure is quite different. This one, 3-fold silicon 3, sp3 bonding, just like bulk silicon carbide. This one, sp2 debonding, fine structure, completely different. Well, I have a couple minutes. I spent about 5, almost 6 years in Singapore, and I was able to persuade JOL not give me, but to sell me a 5th order aberration corrector. Having had a neon, I was not about to go back to 3rd order aberration corrector. So to cut a long story short, they did. And here's Xiao Shu, who was actually there when I arrived and became my student. And this is sub-angstrom information transfer at only 40 kilovolt, as we thought it should be. Xiao Shu thought it was awesome. I thought it was pretty awesome too. Xiao Shu did a lot of nice things. He actually irradiated. He figured out that the electron beam can sputter selenium selectively. He was able to fabricate molybdenum membrane. You can see this is just molybdenum. All the seleniums have been sputtered away, but this is reasonably stable. And it maintains the hexagonal structure that it had in its parent. The Zhao Dong is another student. I just want to mention this very briefly. This is also a 40 kilovolt image, but what Zhao Dong's done here, he's managed to clean it up really beautifully and quantify the density and the distribution of all these point defects. You see, these are selenium vacancies, which he can find by using Zernick polynomials. This is pretty nice, and he can also do far more complicated things here. Here he's locating ion dopants in, let's see what this is. Next to, he can distinguish the ion dopants. He can distinguish the sulfurs next to them in 3 different positions. You can see the tellurium dopants and the tungsten. So this is tungsten disulfide. And you can see all these different dopants here, and you can also see the sulfur vacancy. So it's very nice. It's a very nice way to reduce the noise and automatically find the dopants. And my last student, actually this was my first student, just to show we still do materials studies. In fact, most of the work was on materials, but this is trying to get lead-free piezoelectrics. And this is his crowning achievement here, using thin films of sodium niobate. You get all these translation domain boundaries. And these are incredibly responsive, and you get the largest piezoelectric response so far found. Much larger, in fact, than the lead-based material. And it's also more stable. So this is also a great breakthrough. It was, we patented it, but so that was just a rather rushed run through. Thanks very much to all my wonderful postdocs. I'm sorry I couldn't mention all of them. These are the ORNL group back from 2011. This is the Singapore group 2018. And I think with that, thank you very much. And I better stop here.
Well, Steve, thank you very much for a very exciting talk about all your career-long achievement right here. While the questions are flowing in, please use the Q&A. Let me ask the first one. You have been giving many very exciting examples on the imaging. And based on the Z contrast, based on try to achieve atomic scale resolution. There's so many nice studies right here. The first question is, what's driving each study linked together? You must have a story to tell, right? It's or it's sort of by by this. I wouldn't call it random walk. Just what's exciting coming in, then you're going to look at it. Is there a linkage between all these pieces, in addition to the Z contrast and the atomic scale resolution imaging?
Yeah, that's a very good question. I mean, we always tried to address the issues that were hot at the time. You know, when we started to do grain boundaries, that was a mystery that had not been solved. And then the quasi-crystals, the same thing. And when later times we looked at the 2D materials and finding the point defects. So it's always nice, you know, when you have these new tools, you can address, you know, it's a tool-based program, really. We have fine probe, new techniques, and we try and find the applications where we can solve some long-standing problem. Basically, that's the overall goal. So mostly these topics come from collaborators, and students go and find them. They have their own interests. So it's not really a materials-driven. I mean, it's a materials-driven program in the sense that we want to look at exciting materials, but you know, we're not specific looking at piezoelectrics or anything like that.
Well, thanks, Steve. Certainly, along your career, you have developed many scientists. Actually, many of them I know. Well, thank you for doing that, keeping the whole field going strong.
Yeah, thank you.
Yeah, thank you. So let me ask you a question from the audience. Well, first one from Rafael Duni Bukowski. He says, Steve, were there any features on older VG microscope that are still not available on modern commercial instruments? What can current manufacturers do better?
Oh, well, that's a good question. I mean, the old machines, you know, they did not have the VG instruments. You did not have in those days the variable camera length. You know, even the Philips 400, when I came to Oak Ridge, it was rather easier to go from low angle to high angle because it was, you know, had more lenses. So actually, there's nothing really that was on the machine back then that has not been improved. You know, detectors have got so much better, and yeah, I mean, I can't really think of anything that's not improved.
Yeah, okay. Joe Martis asked, do core electrons potentials contribute to head-up image contrast, or is it just nuclear potentials?
Oh, well, it's basically the atomic potential that scatters to high angles, but the high angle part is dominated by the nucleus. So it's pretty much the nuclear potential, but it's moving around. You know, you can calculate the shape of that potential as a function of collection angle, and you can see it sharpens up. But because of the thermal vibrations, it never gets to, you know, eventually you're seeing the thermally smeared nuclear potential. Yeah, at the limit of very, very high angles. But it's still basically a little bit screened because we never get exactly to the Z squared cross section that it should be if it was completely unscreened.
Mm-hmm. Steve, next one is from Shantanu Lanky. He asks, how do you address the temporal resolution to observe the random atomistic fluctuation, for example, one that is responsible for the white light emission?
Yeah, well, the temporal resolution, you know, and in those days it was just, I guess I forgot to mention, I mean, they were speeded up. So that's about every frame was, I think, 4 seconds or thereabout. And so every frame was a different snapshot of the structure. We don't really have a lot of temporal resolution, but these days you can go faster than that. But, you know, we're not talking about milliseconds or microseconds or anything of that sort. So no, I mean, obviously a scanning instrument does not have very good temporal resolution.
Yeah, Steve, our time is running up. We have 2 minutes. Let me ask a couple more questions.
Okay.
Another one from Kate Rady. She asks, what do you envision as the next big technique development steps for the Z contrast imaging?
Well, I mean, the Z contrast has really come of age, I would say. I don't think, you know, with the aberration corrector and the more efficient detectors we have today, I think it really, the future is putting other signals with it. For example, I mentioned the 4D stem, that's very powerful. And it's still useful, even though you can get all these impressive images, you know, the center of mass images and all of that, very powerful. It's still useful to have a reference image that definitively shows where the heavy lattice is. So I think it'll be useful, even if it's not the most efficient image. Yeah, I mean, there's also the other thing, of course, is the 3D I mentioned. I don't think that's going to 3D through optical sectioning, just change of focus. But I think that's unlikely to really develop very much because we need another generation of aberration correctors to get really down towards the atomic level in 3 dimensions. So, well, you never know, but it could happen, but I think it's unlikely.
Yeah. So Steve, last question. This is from Juan Carlos. I think similar to previous question, maybe broader, right? Just for the electron microscopy for TEM, what direction of development would you like to push first in the future? Maybe it's broader now and not just STEM, right? It's just broader.
Yeah, well, I think combining the signals is very powerful, which I said in the last question, you know, putting the 4D stem with it. And yeah, I mean, you can think of putting in situ as well, you know, you can always get more complicated. You can think of trying to improve that temporal resolution. I can't really think of, you know, I mean, there's Juan Carlos has got all kinds of interesting ideas and plans with phonon, looking at phonon spectroscopy and things like that. Yeah, so there's a lot of possibilities. The EELS resolution, that's been improving, and EELS detectors are getting more and more powerful. Yeah, I mean, and, you know, I showed the Zernick polynomials. You know, you can imagine perhaps setting the microscope to automatically travel around the sample, taking those images, finding the point defects, classifying them automatically. You know, chances you could perhaps have a self-driving microscope, like a self-driving car, that would at least collect a lot of data and let you think about it. Yeah.
Sounds good. Well, thank you so much, Steve. This is wonderful. Bob, back to you.
Yeah, maybe I can ask a question that you might be interested in, Yi. So,
Yes.
Steve, as you know, there have been developments in ABF imaging of light elements like lithium. How do you see that progressing to help with Yi's battery research?
Oh, well, yes, that's a good question. But I think ABF was pretty good as the first way to see the light elements, but the tychography and these new 4D stem techniques actually have a more reliable and more sensitivity than ABF. You know, it's a question of signal to noise ratio. So I think ABF was useful when we only had scintillator detectors, but now that 4D stem's coming along, there are more efficient ways to see the light elements in the presence of the heavy elements.
Yeah, just advertising, Steve, you know, Wah Chu and I, and also Bob and a few others at Stanford right here, we are pushing for cryo-EM usage for material science, for energy.
Oh, yeah.
That's a really interesting direction we are exploring.
Well, you know, one thing I was wondering with the last speaker was tychography, you know, is also quite promising, I think, for biology. It would be quite interesting if you had a 4D stem detector and on your machine, and combining that, you know, you could compare phase contrast with seeing the biological samples by tychography, which is actually theoretically rather more efficient than phase contrast.
Yeah.
But what does Holger think about that?
I think that currently it's not ready for prime time yet, but I'm really curious to see what will happen in a couple of years. Things could go very fast.
Yeah, I agree. I don't think it's been demonstrated yet, but also, you know, it's the contrast transfer function is quite robust. It looks quite like an incoherent contrast function, and it's easy to get the aberrations you want by computer instead of defocus. And so, you know, it's just something to potentially think about.
One of the questions which always arises, Steve, is then, is there any real advantage of having a dedicated stem versus a stem part of it as a TM with more lenses, as you pointed out?
Well, you would know the real advantage is that to overcome that time resolution.
Right.
You really want to see phase transformations in real time. I mean, there's a lot you can do with the stem to speed the scan, and, you know, you can adjust the temperature so things don't happen so fast. But, you know, I think the in situ and time resolution is definitely the sphere of the regular conventional TEM.
Right. I've long been waiting for someone to do the the diffusion of the heavy element individual atoms within a semiconductor using in situ, but no one has really done it in a systematic way and by STEM yet. And so maybe we'll do it if we, since we've been waiting quite a while.
Yeah, that's a great challenge.
A great challenge, and yeah, I'd really like to try in situ STEM when the recording rates and everything gets up there.
Yeah, that's an excellent idea, I would think.
I'm wondering if there's anyone out there who would like to join in, Raphael or Ziwan. Maybe we should stop the recording now and just continue with the informal discussion.